have a next speaker, Vicki from Geological of Canada, and she's going to talk about geological and geophysical integration for regional interpretation of the Western Athabasca Basin.
So I'm going to be talking about some preliminary geophysical and geological interpretations of the new survey we flew in the Western Athabasca Basin. So I'm a potential field geophysicist, but I'm kind of the opposite of Colin, and that I'm trying to learn more geology and to try to make sense of the geophysics by understanding what the geology is doing and the physical rock property variations. So within the Athabasca Basin, the majority of the deposits or resources are defined by deposits on the eastern basin, which until recently, the recent discovery of the triple R deposit in the Patterson Lake Corridor, and these new discoveries in the Patterson Lake Corridor are kind of challenging the accepted exploration model, and this is why the GSC is interested in the area. It's something new and different, and there isn't a lot of information about it so far. From an empirical model standpoint, there are some differences in the eastern model for the unconformity-related uranium deposits versus the western. So, for example, in the east, the deposits are generally 400 meters from the unconformity surface. They're spatially associated with graphitic faults and metamorphic rocks, and sometimes they're associated with paleotopographic highs. In the Patterson Lake area, the deposits are hosted in mafic to ultramafic sheets and orthogneisses up to 900 meters below the unconformity surface. The rocks are intensely silicified and contain hydrothermal graphite and sulfides that predate the uranium mineralization, and the graphitic shear zones were both brittly and ductily deformed. So there's several geophysical and geochemical aspiration models or methods that are used to find these deposits. In the east, so one can assume because the deposits in the west underwent similar processes that they should have a similar signature, properties, and alteration. However, because the deposits in the east or west are basement hosted, they likely have a narrower signature. But there is also data resolution and availability limitations in the west versus east. The east is much more extensively studied, whereas the west is just kind of coming of age. And many of these structures have been altered and deformed multiple times, and this each time has changed the geophysical signatures, the isotopic properties, and the petrophysical properties. So our role as a government organization, we're not interested in the direct detection of deposits, but we're providing the regional framework for the area and developing a geological geophysical model for the area. So the area I'll be talking about today covers the Patterson Lake Corridor and extends into Alberta. So here we have Cretaceous rocks of the Manville group, the non-marine and marine sandstones and shales that overlie Devonian sandstones of the Laloche Formation, and in places overlie the sedimentary rocks of the Athabasca supergroup, and together these cover sequences overlie the dominantly Phanerozoic crystalline basement of the Taltson Domain. And then transecting the main study area, which you can't see on the map because it's buried, is the Clearwater Domain, which was the big, broad aeromagnetic high Colin mentioned in his talk. And this is buried by the Phanerozoic rocks and the Athabasca supergroup. So because of this extensive cover in the area, we need geophysics to figure out what's going on in the basement geology. So in the 2017, the GSC flew a new aeromagnetic survey to inform these interpretations, as well as try to get some information on the regional structure. So I'll be going over some of these preliminary interpretations that are very much a work in progress of the new magnetic survey, incorporating some rock property measurements I took this summer, as well as geological information I've got from either talking to Colin and other geologists and digging through the assessment files that are located online for the drill cores that I logged. And to demonstrate the value added by taking an integrated approach to the geophysical interpretation of the mag data. So the existing data before the GSC flew the survey was the 400-meter compilation grid that was flown through, I think, the late 2000s over the Athabasca, but stops just short of the basin margins and does not continue on into Alberta. South of the basin and in Alberta, you only have the 805 meter space legacy data that was taken in the 70s. It's analog. It's pretty messy, but you can still, you start to see there's broad trends there, so you can make some interpretations. The new survey, the Marguerite River Survey, which is available for download to all those interested through the DAP repository or through the NRCan website, was designed to infill the 2008 survey to create a 200-meter line space grid, as well as 250 meters over the areas that were previously 800 meters. As well, we produced the first vertical derivative maps, which is also available for download. The tilt derivative, or the tilt angle, which is available for download, and the heating correlation coefficient results, just because of the kimberlite hype that was going on last year, seeing if we could identify any circular magnetic anomaly. There's a couple that, but they could be something else that I'll talk about later. So the way to link the geology to geophysics is rock properties, and I always tout this. So magnetics, where we care about the magnetic susceptibility, the gravity density, and EM conductivity. And these measurements provide the statistical information on the rock unit, so any variations, and we'll start to get an idea of the distribution of rock property values for distinct lithological units that we can use for interpretation and modeling. So by identifying what rocks are causing the anomalies, we can extrapolate these below all the cover sequence and begin to construct magnetic lithological maps. Okay, so I'm just going to go over some of the rock property information on the public available drill hole data for this area. So this summer I logged several regional drill hole data for magnetic susceptibility, as well as digging through assessment files to get geological information. And so the first one is right along the Beatty River shear zone, and the magnetic anomaly is caused by a monazite unit located near the bottom of the drill hole. And this also, so before I started going through the data, I was doing Euler on the MAG to see if I could get an idea of the depth, because I gridded the drill holes to get a basement surface, and then there was a couple of gaps that had distinct linear anomalies in it, so I wanted to see if I could do Euler on it to essentially poke a data point in the hole, and then all the data was off by a couple hundred meters, the drill hole data versus the Euler solutions over the same area. And then logging the drill hole made me realize that these magnetic units were sometimes like 100 meters below the unconformity surface. So our Euler depth estimates weren't actually the basement, they were below the basement. So you have to keep that in mind when you're doing depth. There's a little lesson learned for myself from doing depth, that it's not always magnetic rocks at the unconformity surface, so you have to be aware of if they're buried or not. The second hole is over this folded magnetic body, and you can start to see the variations that are somewhat correlative with the broad geophysical signature. We've got the lows and highs. Oh, so the red is the unconformity surface, and the blue line is the Manville cover. And you can start to pick up more variations that you can kind of see in the magnetic map, the undulating lows and highs. Down in this area, you get the same amount, but it's much more subdued. Both these drill core have the granitic orthogneisses and metasedimentary gneiss, and the magnetic anomalies were generally within the metasedimentary gneiss area of the drill hole. And the fourth hole in an area of it's right here, subdued magnetic response is again reflected in the physical properties. There's not a lot of variations going on. It works nice with what I was seeing in the broader magnetic picture. So I want to enhance the contrast that I'm seeing. So because of the area, the sedimentary basin, and then in places Phanerozoic cover, there's a lot of attenuation going on, so in the total field map you're not getting the details. So this is why we use source edge detection methods that Omid went into some detail on. And these essentially are a series of mathematical algorithms that maximize some source function over the edge. And depending on the method, they respond differently to different geometries, and they reflect the maxima of the source edge detection methods reflect different things. So for example, the tilt zero contact is the edge of the source, and it's positive over the magnetic source, whereas something like the total field horizontal gradient is a maxima at the edges of the source. So they all respond differently, and you want to look at a lot of different methods when you're doing it. You don't want to put all your eggs in one basket and just make your interpretations from one source edge, because they do respond differently. So for the effectiveness varies, and it also varies on the depth of the source. So Omid mentioned that the tilt was better for deep sources, and you can really see this when you look at the analytic signal and the total field horizontal gradient. The Clearwater Domain, which we know is buried and likely deep because it's a big gravity anomaly, you can't see that at all in these methods, whereas it stands out nicely in the tilt and first vertical derivative, and it's a broader anomaly on the reduced to pole method. So this is again emphasizing why you want to use multiple methods. And then another trick, going back to Dave Thomas's comment about remnants, one of the first go-tos for trying to identify remnants without actually drilling was a paper by my colleagues of yesteryear, Walter Rouse and Mark Pilkington, who argued that because the analytic signal was insensitive to the remnants direction, if you looked at whereas the total field horizontal gradient maxima is sensitive to the remnants direction, you tried to look for if there is differences in the anomaly shape when you draped them on each other. And this could be kind of a first pass if you're looking at anomalies to see if they work with each other, if the analytic signal is working with the total field horizontal gradient, and if that's working with your reduced to pole magnetic field. So in my experience, I like tilt a lot, but I also like total field horizontal gradient, and bringing the two together to visualize the textural variations, especially the near surface features. So here's some ways I visualize my data. So the first one is the tilt over the digital elevation model, and displaying the magnetic methods over the DEM can give you an idea of what structures could have been possibly reactivated. So are you seeing lineaments and discontinuities in the DEM that are also present in the magnetic image? And this can also be applied to your radiometric grids or geochemical grids, or are there any lineaments that are associated with radon anomalies, trying to see if it's expressed in multiple layers. As well as for looking at the DEM and drawing structures, it's helpful to display the sun angle at multiple orientations, because depending on the orientation, you're going to be picking out different orientations of structure. And then the tilt, total field horizontal gradient over the tilt, I like it. I think it really brings out some of the near surface features. So when I was pouring through the data initially, when they were flying the survey, in the MAG, you can start to pick out paleofluvial features in it. You can see paleo valleys that are very high frequency, and they don't work with the basement geology, so they're floating somewhere between the unconformity surface and the surface ground. And they're all very complementary with each other. So from these source edge detection methods, you start to get structural information from them and define these magnetic lithological domain boundaries, because we're not mapping lithology necessarily, we're mapping magnetic domains that may or may not have the same geological contact. So this means the distribution of faults enfolds the orientation, the spacing. If you have discrete magnetic marker units, you can look for relative displacement and get an idea of that, as well as the fault timing, fault offsets, and some of the ages of the faults, if you know how old the units that they're offsetting are. And then bringing all this information together, you can begin to draw lines on your map. So to extrapolate below the sedimentary cover and define these magnetic lithological domains, because they could be the same geology. And then start drawing lines on the map, so bringing in your lineaments and discontinuities to give it structure. So starting from the top, several of the drill holes I logged had Phanerozoic cover in it, and I wanted to see if there was magnetic anomalies that would presumably be coming from the Phanerozoic cover. So this is the Manville group units, and then the Lalache Formation sandstone. So this is just a box and whisker plot of some of the magnetic susceptibility information. And from the Manville group, it was generally more magnetic than the Athabasca group, and it also had anomalous layers in it. And at times, in some of the holes I log in the fairly subdued gneissic basement, the Manville was the most magnetic unit in that hole, and there was even boulders and like pretty decent sized horizons of quite high magnetization, and these would be giving it that stippled anomaly that's overlying the basement. And you can see, even just looking at the map, so this area is below the Phanerozoic cover. This is just under the sandstone, and it's much more textured, especially in the high frequency domain. So is this the Phanerozoic cover that we're looking at, whereas this is just a nicer, cleaner sandstone? And that's on the eastern side of the Clearwater. And so this is the Clearwater Domain. And so this is the Bouguer gravity anomaly map draped underneath of it, and some contours. So you can get an idea of the anomalies over the magnetic field image. So even though it's not that magnetic, the Clearwater Domain is fairly pronounced on the aeromagnetic map. It's a big feature. And it has a bigger gravity low associated with it. And the gravity stations are 10 to 15 kilometers. So the feature is at least 20 to 25 kilometers wide because of this. And so I've logged a few drill holes that were over the Clearwater granites, and none of it was magnetic. It was the same magnetization as the Manville cover that was overlying it, which suggests that something is a deeper source, a deeper magnetic source that maintains this low density is located below the cover. As well as, so the gravity data, you've got highs to the east and to the west over magnetic highs. And so even though this is all the same unit, are we seeing compositional variations that's being reflected in the gravity and magnetic data? So it's all Taltson Domain orthogneisses, but where it's over the gravity highs, are these more mafic in composition? Are these rocks more dioritic versus granite and granodiorite? And a good example of this, so this is the Margaret River complex here, and so it's a much more subdued magnetic rock, but it's also got a subtle but present gravity low associated with it, and these rocks have been mapped as granodiorite. And then, so this is the analytic signal, again showing that you can't really see the Clearwater Domain, but you do have later intrusions that come up along it that are potentially magnetic in that surface. So it would be interesting to see if these could be followed up, and if these rocks that are closer to surface are reflective of the rocks that are buried. So this is the Clearwater, or the Margaret River complex I just mentioned, and these are, our postdoc is doing some geochronology work on the area, and so he dated these samples a couple weeks ago, and they're 1.97, which is correlative with the Collins Lake granodiorite and Fritching Creek granodiorite north of the basin. And so one of the things I was worried about when I made my interpretation, I included the magnetic edges along this side, because there was a shear zone mapped here, and they fit with each other in this lozenge. And then when he plotted that date on that unit, I felt really good about my interpretation that I had called it granodiorite. And then you can start to trace these through the basin along here. And then looking at, so this is getting into the whole protolith mapping. So here's the Clearwater Domain, and this is all the Taltson Domain orthogneisses, and these are the same rocks. They're compositionally and geochemically similar, but they're their magnetic characteristics are very different, as well as their rock property characteristics are very different. We've got the subdued gneiss up in this area, the undulating magnetic highs and lows over number 2, and then in the Patterson Lake Corridor. I took one of the examples from one of the aeromagnetic highs, and you have the magnetic highs associated with it as well. And these were all orthogneiss in outcrop with varying levels of felsic to mafic orthogneiss. And this is why it can be difficult when you're making these remote predictive maps and assigning lithologies to these units, because they look different, but they're the same. Essentially, a geologist would map them as the same. And it's important to be aware of what's causing these differences. And so some of what I've encountered for causing these differences is due to the alteration in magnetic or metamorphic histories, and this changes the geophysical signature and rock property characteristics. So when magnetite is oxidized to hematite, it causes a reduction in the bulk magnetic susceptibility of the rock. As well, there could be just compositional variations, so granodiorite versus more dioritic composition in the rocks. And then as well, one of the studies I did when I first started at the GSC was in the Baffin Island on some granulate facies metamorphic rocks, which when you walked over on outcrop were a relatively homogeneous unit. And then when the metamorphic petrologist did the PT work on it, he found that the rocks were at the stability limits of magnetite. So you had these complex patterns on the geophysical image of essentially the same unit, and it overlapped the magnetite stability conditions. So these are kind of the ugly to be aware of. Like, we have our postdoc will be doing some pressure temperature work, as well as looking at the alteration assemblages, so we can hopefully get a better idea of what's going on here. So, and then on a more local scale, we can start to pick out, by having logged rock property magnetic susceptibility on the core, what is causing these anomalies. So one of the things, some of the lower cores we logged were carbonatites, and they had a surrounding phenatized alteration zone, which was associated with mag high. And these were magnetic highs on the map, as well as some ultramafic rocks. So while even these were altered, they were still a relative high compared to the surrounding altered rocks. And the non-altered rocks themselves were the most pronounced signal on the map, and they're the shorter elongate anomalies. And when I was interpreting these tiny little anomalies, I was really worried that they were due to human features, and I had found people's drills. But when the GSC records all the flight footage on it, so I had people go through to make sure that they were actually anomalies and not flying over someone's camp, which was nice, because there's even more of these point anomalies in the south towards the triple R and and arrow deposits. Look at the flight. If you're ever not sure about that it's actually anomalous, look at the flight footage to make sure that there's nothing there. So the next steps, I'm going to refine the preliminary interpretations, start putting pen to the paper, drawing some structure, and then is statistically characterizing the rock properties. So one of the things, remnance is important. It needs to be dealt with and considered. So this summer I took samples of hematite, pyrrhotite, and magnetite bearing rocks to see if we can get an idea of if there is a remnants factor that we need to worry about. And then I want to get an idea of the effects of alteration on the geophysical signature, especially in the Patterson Lake area, which is where I'll be moving into working next. So they already went through the geophysical anomalies you're looking for. It has the triple R deposits and prospects, so you're the disrupted or violated V-chem conductor, an edge of a magnetic anomaly, and then gravity low alteration halo. This gets more complicated when you step outside of the basin where you're dealing with the Phanerozoic cover, the glacial overburden, and the Athabasca sandstone. And then if you have an alteration halo thrown on top of that, it'd be an interesting interpretation. And then the radiometric anomaly, such as a boulder train. So in the Patterson Lake Corridor, we've got these orthogneisses ranging from dioritic in composition to more granite that have been intruded by younger mafic and ultramafic sheets. So in all of these units are variably magnetic to non-magnetic, with or without sulfides depending. So one of the things we noticed when we started to plot stuff, one of the great things about having a summer student is I made her go through everyone's assessment file and presentation and digitize all of the conductors. So we can get an idea of how the conductors relate to the magnetic lineaments, and if they aren't related, why is that? Are the conductors reflecting structures? Or if the magnetic highs, which are ultramafics, that host sulfides, would these be causing a conductor as well? And a lot of the deposits are located at these conductor breaks at the edge of a magnetic lineament. So what is causing these anomalies? We want to get a better understanding. And then can we see this anywhere else? So we need to take a step back and see if there's any regional trends that we're looking for in this area. So when used with geological information, I think you can get a lot more out of your geophysical interpretations. So using this new aeromagnetic data to refine the maps and to get magnetic susceptibility information, and if possible, get remnants information. So I'll be looking at some 3D models of the magnetic data in the Patterson Lake Corridor. So we want to make sure that we're accounting for any variations in the remnant or the magnetization vector. And then we need to have a better understanding of the effect of the geological processes, and so alteration and metamorphism, and how these may affect the geophysical signal that we're seeing. So thank you, and thank you to TGI5 and all the companies such as PurePoint, Forum, NextGen, and Fission that are helping out with this project. Thank you.
We have 2 minutes for any questions.
Can we get copies of these talks? You can.
Yeah, Ken was talking
Yeah.
about that.
Ken,
Well, the
I
Andrews and
believe
the-
Ken gave us a copy. Is that right?
Ken was saying before you got in that he's going to make.
It's being recorded.
Yeah.
Okay.
We have to transcribe.
Dave?
I just want to say, nice piece of work there. I really like what you did with layering the elevation data on your magnetics. Showed the strength of doing a simple exercise like that and interpreting some of those shallow features, those dimply, stipple
Yeah.
things that always confuse me.
You're like, is it a drumline? Is it not a drumline? Because
Yeah.
sometimes it is.
Yeah, or now it could be Mando.
Yeah.
So a nice piece of work there.
Thank you.
Thanks, Vicki.